problems, what kind of tools Matlab provides. Okay, are there any issues you would like to discuss before we start the lecture?
I have a question. Can you hear me?
Yeah,
When can we expect the laboratories, next laboratories? I mean, on the website, the
this
lecture as well.
uh, probably today.
Okay.
I, I have sent, I asked Dr. Mushinsky to update, to put the slides on the web page. So
Thanks.
probably today you will have the description of the task and the lectures. Anything else?
Hello, sir.
Yep.
I want to ask about the last lab,
Yes.
last group. Sir, we are there in the group like 310, but you tell me you have to mail. But how can we know that you are coming or not? We
Mm.
mail about
I don't
last
know.
lab.
There was during the last lab there was some issue with this one group Zoom. I don't know what happened,
Yes.
and you will know like the same like you know right now, right? When you will just
No, sir.
log.
We mail to you 2 times, me and my friend also. But you tell me the rule will remain same. But we are there. We are waiting for you.
Well, maybe we should clear something here with all of you. So the thing is that we doing this remotely, right? So
Yes.
sometimes those connections may go wrong. I don't know, something may happen wrong on my side or on your side. And it means that it doesn't mean that the lab is not valid. I mean, you need to deliver everything that was agreed on the lab or what I ask you to deliver. So there is a description of the task on the web page, right? You work in your home, you don't work in the lab. In
Yes, yes, sir.
so
We give everything.
you are not restricted anyhow. And I also said that if you won't make to check the results during the lab, you need to send me the results via email at the end of the lab. So even if there was some issue with connection, there is no reason why you shouldn't send me the results of your work, right? Because
Yes,
even if we haven't connect via Zoom, you work on your PC at your home, and you should have the solution there, right?
yes, sir. But we are still waiting for you like half an hour. But we don't know like
But
we have to.
the rules are
Okay.
the same. You need to send. You are obligated to send me the solution, the latest at the end of the lab. This is the
Yes, sir.
latest
But
time you can send me the result.
yes, I know everything. But then we mail
Okay.
also on that time. But now we have only two guys in that group which are active, and we have did on second lab everything. So can you give me just 1 hour like to submit our solutions?
No, I mean the rules are the same for all. You need to send solution at the end of the lab. That's it. The
Yes,
rules
sir.
are all for all the same.
But
So
we are still there like half an hour, like 16 till 45 minutes. We are waiting for
okay,
you.
okay, and so what do you want to say that we weren't able to connect, and even though you
And
should and you even though you should provide the solution.
yes, sir, then we mail. We both guys are discuss and we then mail you like solution and we just answer you by the mail. But it's later. It's out of time. I know it's out of time.
So I don't know why
But
you're waiting so long with
but
sending the solution.
but evening we both mail you with solutions also. You can check mails our.
Probably you can discuss this during the next lab.
Okay, okay.
What we can do with that. But
Okay, okay,
generally,
okay.
rules are simple. You are not
Okay.
working on the university computers. You work on your PC. So I assume you have access to your PC. You can do your job and send me the solution. That's it.
Okay,
If
so
you need
then,
some consultation, we can meet in other time for
okay,
consultation.
okay, thank you so much.
Okay. Okay, anything else?
And
Okay, so let's start the lecture. So, numerical methods. Let's see what it means. I will read I will read just the definition. I would like to not um, avoid to mention or forget to mention some uh, important things. So let's check what does it means. So generally, numerical methods generally it means that they do some numerical approximation of the continuous problem. So we will approximate somehow the solution. It won't be the exact solution, right? You using the numerical method, you need to be aware that solution you'll get will be some kind of approximation, uh, not the exact solution that you get from the just solving the analytically some kind of mathematical problem. This is the first thing. Generally, this numerical methods. This is a branch of mathematics in general. There is a field within the mathematics that try to deal with different numerical methods. Um, and what we need to also know that many of the problems are very hard solvable, or we don't have solution for some of the problems. And in this case, the numerical method can jump and try to deliver some approximated solution, because there are many problems that you can't, there is just no, we don't know the analytical solution, right? So you can't write the equation which will describe what is the solution of some formula. Um, the In fact, when you look at the complexity of the problems we deal with in engineering or in science, generally analytically we can maybe solve some very small amount number of problems, very very small. Uh, but in the real life scenarios, unfortunately, you need to deal with the complex problems, and you need to deliver those solutions very fast. So generally, in most cases, we can say that engineering, the mathematical foundation of the engineering, use the numerical methods. When you implement some controls, you estimate, you try to solve some equation in some in industry or in the robotics or in the automotive. Most cases probably you will apply some kind of numerical methods. Of course, if you need to deal with this kind of problems, I hope you will need to, because those problems are really interesting. Okay, so what the numerical method means. So the numerical analysis is a branch of mathematics that solves continuous problems using numerical approximation. It involves the design methods to give approximate but accurate numerical solutions. So we design the methods which are close to the original solution, right? We are not interested if any to get any solution, but we would like to be as close as possible. And probably, as you can expect, the better accuracy you achieve, you need to perform more steps, some more numerical iteration to get closer and closer and closer to the final solution. But probably you reach the optimal solution or the best solution somewhere in the infinite, or when you reach the numerical limits of your machine. So you'll be as close as possible, but not closer, because your machine is not possible to provide the exact solution in this case. And this numerical solution, which is maybe useful in case where the exact solution is impossible or prohibitively expensive to calculate. So you can imagine that maybe you can have some analytical solution, but it will take, I mean, writing this solution in the form of the equation will take, I don't know, 4 or 5 pages of R4 paper. So this is typical situation in robotics when you write down the model of the dynamics. So when you try to describe how the motion which looks like when you apply the torques to the joints. So the formulas that describe the motion of this of let's say 7 degree of freedom manipulator is so complex that you require number of pages to write those formulas. It's very easy to make the bug somewhere, right? You can forgot to add some important coefficient and the whole solution will be wrong. So there are those two situations when we need those numerical methods. First is when we know that or we don't know the analytical solution because someone prove or we just don't have this solution. So we need to apply the numerical methods which give us some approximation. Or the second, also very common, that there exists solution, but writing the formula will be very difficult and we don't want to do it, right? Okay, so numerical analysis also involves the characterizing the convergence, accuracy, stability, and computational complexity of those methods. So this is something that describe the the numerical methods. Because when you design the methods, numerical methods, first you need to guarantee that when you apply this method, the solution converges to some final solution or to the truth solution, right? So there need to be a convergence when you look at the error plot, right? It needs to vanish somewhere in the infinity when this is error of the method. So what we expect that when we iterate, right, we do the iteration. In each iteration, this error will be lower, 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 lower. This way, when we go to infinity with the number of steps, our solution is close to the original one. The next one is accuracy, which describe how good we approximate the final solution. What is this final error? Because different methods can give different accuracies. Typically, uh, when the problem is very complex, uh, like have very large number of independent variables, I need to search multi-dimensional space because the space of the parameters can be really multidimensional, right? So looking for the solution in this kind of space is time consuming and sometimes is NP hard problem. So we also some numerical methods just use some heuristics, and based on these heuristics, the accuracy we achieve can be better or worse. So depending on how good the heuristic is, we can have a better or worse accuracy. The next one is stability, and somehow it is related to the convergence. There are methods when you optimize nonlinear system, you have some nonlinear function. Let's draw it a little bit more carefully. Okay, so let's try. Okay, let's do it maybe mm, like this. When we can. Okay, let's discuss this guy. So the some numerical problems, or most of them are local. So they look for the solution. Probably there is a large number of methods use the Jacobian or gradient of the function and go along the gradient. So if you will select two large steps and you do two large steps, you can jump between, if you are in the local minima, you can jump between 2 points and never get to the minima. Um, or even you can, if the function is very fast change and the gradient is large, this step can be so large that you overjump the to some different position, and you can jump this way depending on how the function is built. And some of the problems, I mean some of the methods are not stable or can't be applied to any kind of problems. So this is something that you need to also be aware that some of the methods, numerical method that you will use, maybe not, maybe or are not stable, and this means that you can't use them in machines or in the place you would like to you would like to apply, or you need this kind of solution somehow. So this is very important for from the engineering perspective, because you will deal with some real life scenarios, and there exist many of different methods to solve some problems, but at the end you will need to select methods which guarantee the stability in given region. So you need to guarantee that no matter what happens with your system, the system will always give the stable solutions. Okay. The next thing, also a very important, computational complexity. As I said, you can deal with multidimensional problems, and depending on the complexity, some of the methods may be used, let's say, on the desktop as a method for, let's call them offline. You can solve some problem offline, right? And then in the offline problem, you don't need to take care too much about complexity. You can wait 1, 2, or even several days to get the solution, right? But in the working machines, probably you need to be very careful with selecting the methods, because probably you will need to deliver some kind of solution, let's say in 1 millisecond or 10 milliseconds, because this can be a bit horizon of the control. And when you get the update from the sensor, in next, let's say 1, 2, or 5 milliseconds, you will need to solve some optimization problem again, right? So you have, let's say, 10 milliseconds to solve some complex optimization or route finding problem, or different problems depending on the scenarios. So this is what we will talk about. Maybe not about how those methods are built, but how to use some of those methods in MATLAB. Okay, so what kind of numerical methods MATLAB can solve for you? So first, widely applied, very important, is interpolation, extrapolation, and regression. Regression, very very important when you identify the models, or you want to process some you would like to build the vision systems. Regression is one of the major tools used in this kind of problems. Differentiation and integration, this is something that you can also do numerically. Solving the linear system of equation, right? So this is in fact the root finding problem, type of is equal b, right? This is uh, eigenvalues and singular values, computing the singular values and singular vectors, uh, or doing the eigenvalue decomposition. And the next one, very important, is the ordinary differential equation. This is what we will talk about in more details during this lecture. Uh, Partial differential equation, this is something that will be not covered in this lecture, but can be also solvable with MATLAB. And last but not least is optimization, which we will cover partially. We'll try to explain how you can solve linear and nonlinear optimization problem with linear and nonlinear constraints. There are also different methods, variety of numerical methods. Generally, whole Matlab is designed for solving the numerical methods, but those listed here are the most important. I mean, the basic, the essential, let's say, looking from the engineering perspective. When you look at the problems you need to deal with, the as an engineer, this is the range of the basic stuff you need to know how to solve. I mean, all of the others are based somehow on top of those simple problems which we will discuss here. Uh, we'll talk all about this ordinary differential equation and optimization because those are the iterative method which we need to know a little bit more how to use them properly. All other problems are kind of, let's say, one method call. So MATLAB just implement those the methods for solving these problems. They are not very complex. It's very simple. I mean, from the user perspective, just one function code. They are not much to say more than is written in the help. But the ordinary differential equation optimization, this is something that needs to be explained in more details. Okay. So, moving forward with this numerical integration and differentiation, we have in fact several different types of problems we can deal with. So first is the ordinary differential equation. So in this case, typically we solve the initial value problem. So I don't remember. I have this somewhere later. Okay, let's discuss this here. So who knows what the initial value problem is? Have you heard about this kind of problem? So we have some, let's say, differential equation. Okay, maybe we can have time also and some control. And what is the initial value problem? So we have some equation, differential equation, and who knows what kind of problem we can solve, how to solve this. Anything? Okay, so the initial value problem is one of the most common problems we solve in most cases, and it consists of you have some initial state of the system. Let's say this is your xy plane, so the state is xy. This is your state. Oh, I should use different notation here to avoid confusion. So this is the state. So you are somewhere on the plane, and what you want to know is how the system will evolve on some given time horizon. So you have time from, let's say, 0 to t, but this can be any time. And we want to know how the system will evolve in time. In fact, what will be the flow of the system? We call this flow of the system on the time t and applied control u. Okay, we have u. So we have some system, we apply some control, and the system start moving. Like this can be a robot, like can be a mobile robot, right? We have two wheels. This is, let's say, differential drive robot. We can control the left and right arm wheel, and by changing the velocity of the wheels, we can modify the path of the robot or trajectory of the robot. So when you describe this robot as a differential equation, you can, using this solver, you can simulate how the robot will move on the plane when you apply the control. This is the, in fact, very common major problem we need to solve numerically. Second one is in boundary value problem. What you know initial and final condition, and you want to know how the system was evaluating in time uh, between those 2 points. And this is very complex problem. The initial value problem is simple. There are a number of methods that solve this problem, and it's in most cases is solvable. There is no big deal to solve the or initial value problem. But boundary value problem is quite difficult, and they may not exist the solution. So we are not sure that we will be able to deliver a solution even if we will select the best methods available on the market. There are also problems like Glade differential equation, partial differential equation, and last but not least, this is numerical integration and differentiation. So this typically works on the samples. So you have samples, 2, 3, 4, and you want to compute the integral of the samples, or you want to compute the derivative of the samples to get the velocity. So Matlab give you the method to numerically integrate or uh, differentiate some data set. So this is what you can do with the Matlab. Um, we'll focus on this ordinary differential equation because this is in my opinion, one of the major tools that is used by engineer. So what is this ordinary differential equation? So it contains one or more derivatives, and there is a dependent variable of some degree, right? Um, uh, and we have dependent, and let's say call it y, and have single independent variable. Typically we call it this t, which in most cases means time, but it doesn't need to mean the time. It's just something that evolve independently. And in fact, we have dependency like this, that y is the function of this independent variable t. And the derivative of y with respect to t, okay, let's call it dy dt, we will note with like this, and the higher derivatives will just add another mark here. So this will be our notation, and this is standard notation in math. So this is how you typically write the differential equation. So we have second order differential equation, which we can write like this, right? And this means that we have second order derivative dt dy dt minus 2y is equal to 0, right? This is more or less what it means. Okay. And side note that we call the order of the differential equation is the order of the highest derivative in the equation, right? So this is the second order derivative. If we will have third order, so this will be the third order. Even if there are also lower order derivatives in the equation. So, as I already said, the initial value problem consists of finding the solution or evaluation of the state when you start from initial condition y0, right? We have some y0, and we look for the solution over some period t0, tf. This is our time to which we we ask the solver to give the solution, and the solution will be provided iteratively. Um, and what you maybe is this is the internals, but we can say that the initial value problem is solved for ODEs is solved numerically by the iterative algorithm, and uh, each iteration requires some evaluation of the original function. And depending on the complexity of algorithm, you need to, I mean, the algorithm will need to evaluate this function more or less time, what is somehow related related to the CPU time, the total time required to deliver the solution. So the higher accuracy you can expect to achieve the higher accuracy, you will need to spend more time or have better, more powerful CPUs to deliver the solution at the same time. Or you will need to just spend more time for the solution. And the solver, it used uh, some information of the function at current step, and also use information from the previous step. So this is why the algorithm is iterative. You can't just omit some steps in the iteration, because these previous values are quite important for the algorithm. Um, okay. Um, and what the solver do, it provides you the vector of solution. So you have some differential equation, which is, let's say, y. Okay, we can have some control, and when you call solve f, right? So you need to provide the initial value, right? You need to provide the mm, time vector of time at which you will ask for solution, and at the end you will get the vector of solution y at each point, right? Let's say this was t0 to tf, and solver can also provide you the vector of times at which it was sampled the solution. I will discuss this later, because you can give here the only the range. So you can say give me the solution on time 0 to, let's say, 2 seconds, but it doesn't mean that you will get only two samples at the end. Solver will give you all the samples that was taken or computed during the integration. So you will get vector of the solution and vector of the times at which those solutions were sampled, or you can specify each time at which you are interested with the solution, and then solver, I mean this result vector will be the same like input vector. You need to be aware that probably solver will need to interpolate. So like when the solver sample the solution, it doesn't make the constant step. So those steps dt, well, assuming this is time, so dt can be different for each step, t1, t2, and so on. So this dt can be larger or smaller, and when you, let's say, specify some time like t1, t2, t3, it doesn't mean that solver perfectly will compute the solution exactly for this time point. Sometimes it take smaller or larger steps, and if it won't, let's say, if you want to select this time that you provided as an input, if it won't compute the solution at this time, you will have some solution between. So you need to interpolate the solution for a given time. So this is some additional. It requires some additional processing after the finding the solution, numerical solution. But this is a specific feature of the solver. Not very important right now. Okay, so mm, MATLAB typically expect some form of the differential equation. It means that you can't provide the differential equation in any form, like, because you can, on the paper you can write very complex uh, equation, right? But no, it doesn't mean that you can provide this formula to the MATLAB. MATLAB expects some form of the equation, and the typical form for most solvers that are available in MATLAB is the first order differential equation. So MATLAB expect that you will write a function or the right hand side of the differential equation in the form of the first order differential equation, and the equation is explicit. So you have first order derivative on the left side, and you have the function uh, on the right side. This is the form which MATLAB expect, and you can use this form in any solver which is available in the MATLAB. Some of the solvers can also expect this linear implicit order. It means that you can specify your differential equation in the form of the first order differential equation, and you provide some um, non-singular mass matrix. This is very common in the dynamics in robotics when you write the differential equation of motion for the manipulator. You have something like, you have the inertial matrix plus Coriolis plus some let's call it uh, gravity, and we have external forces on this side. So this is this mass matrix. So you need to move all these things to this side, to the left side, and um, write the whole system as the first order differential equation. So I will explain how to do it in a minute. And you don't need to numerically inverse this matrix, right? Because when you want to write this equation in this form, you will need to write it like this, right? Oops, sorry, Ty. You need to numerically inverse the matrix, which in most cases is not a good idea because it can be singular or close to singular. So in this case, you can use this implicit linear form of differential equation, and the solution of the systems will be taken by the solver afterwards. Okay, so we have those two forms. So this one is the basic one. Some of the solvers can also take this form. But this is not all we can, not all forms we can use in MATLAB. MATLAB also is able to deal with the differential algebraic equation. This is some let's say special form of the ordinary differential equation. So in ordinary differential equation we have only this part, right, which is standard differential equation, but differential algebraic equation, this is system of equation which includes the ordinary differential equation and so some additional uh, system which uh, is not differential equation, right? It's written in this form, and unfortunately, this is much more complicated problem to solve than ordinary differential equation. Only several subsystems or types of systems can be solved numerically. DE systems can be solved numerically. Um, I mean, if you can, it's best to avoid this kind of problem. Sometimes it's impossible, of course, but it's much more computationally complex. You need to apply much more complex methods, and the solution can not exist, because what you guarantee here is that at any point of time, right? At any point of time when you compute the evaluation of the system, having this exists always, right? So you can always compute, or in most cases, you can compute the if this is let's say continuous and so on and so forth. We can compute the derivative, so it means that we know in which direction our system evolve, and we can go along this direction, right? With smaller or larger steps. This is how it works. But in this differential algebraic equation, you need to guarantee before you will take it's not, I mean, the direction is one thing, right? This is this part. But you can't execute the step in this direction when this function is not true. So the g is not equal to 0. So you need to make sure that at any point when you move in this direction, also this holds. And this is not always true. Um, okay, so that's it about the DA. And the last form that MATLABs can, I mean, which MATLAB provides the solution, for which MATLAB provides the solution, is the implicit ODE. But the implicit ODE, I mean, there is probably only one or two solvers which can deal with the implicit ODEs, and this is the case when you can't just put out the derivative outside the function, like your derivative is non-linearly dependent. You have some complex function which depends on the derivative, and in this case you can't just recompute or rewrite the function f to take this derivative outside the f function. So in this case, you need to solve the function implicitly. And this case is also a little bit more complex. The methods that are applied are much complex, much more computationally expensive. And well, the solutions are, it's harder to get the solution. But you can try, right? This is what MATLAB provides. From my perspective, what I can say that it's best to have the system in the form of the first order differential equation. So this is the typical formula that MATLAB can deal, or not only MATLAB, but when you will look to the numerical methods also in other systems, like in Python, you would like to solve the ordinary differential equation, or even C++ or C, the libraries that implement the solvers, numerical solvers for ODE, expect this kind of form of the differential equation, first order differential equation. That's it. Okay, so this is about the differential equation. And what we will solve the system of differential or ordinary differential equations. So the systems means that we have number of differential equations which define our system, not only one. This is like solving the system of linear equation, but in this case we have a system of ordinary differential equation. And this is what we in fact will be solving in our case. Okay, so let's talk about the how to how to how to write any high order differential equation as a first order differential equation, because this is the something that you need to learn how to do it, and you need to also uh, this knowledge during the lab, because the form of the equation which we will deal of during the lab will be the second order, and you need to know how to write those equations as the first order differential equation to apply the solver. Okay. Um, as I said, the solvers, ODE solvers mostly solve the first order differential equation, and you need to somehow rewrite this equation. And the approach is very simple. So you introduce some additional dependent variables. So before we had the variable y, right? And right now we assign or we introduce new variable for each order of the derivative. So the y will be the y1, uh, first derivative will be y2, second will be y3, and so on and so forth. So we'll have n minus 1 additional variables. So if we have second order derivative or differential equation, we'll have y1, y and y1, right? Sorry, y1 and y2. Okay. Um, because this will be our y, and this will be the velocity, the first order derivative. And when you introduce this new variables, you need to rewrite your differential equation in this form. So as you see, we have the chain of equation. So before we had the one, let's say we had the one, let's assume we had some equation, right? And we have introduced y1 is equal y and y2 is equal. So right now we need to rewrite the equation in this form. So we have some additional equation which describe the dependency between variables. So y1 prime, right? 1 y prime. What does it mean? It is, sorry, I too much. So here we have what? y2 is, so y2 is the, so this is the first order derivative, this is this, right? And we write that this is uh, the derivative of the y1, and y1 is y, so this is just, so this is equal, right? We write that first derivative of y is equal first derivative of y, so this is true, right? But in the case of the variables, we have this dependency, right? That y1 derivative is equal y2, because this is y prime and this is y, and prime means is equal, and so on and so forth. So this is this is the chain true for each derivative, right? That the lower variable number is derivative of the higher, right? So y2 prime is y3, y3 prime is y4, and so forth, and so on and so forth. Okay, this is how it works. And at the end, we have the last equation, which in fact is we need to rewrite this original equation, right? This was our equation. So we need to rewrite it in the form or use or we need to express this equation in terms of these new variables. So in this case, we had what? This is our, this is just y2, right? So it means that this is uh, derivative of the y2, right? This is equal. So we need to write that y2 prime is equal to f of what? What we had? We had y1, y2, and this will be what? This is y, this is this, so it will be equal to minus y1. Okay, I have example on the next slide, so we can do it again on the next slide. So here is an example. Um, this is our example, third order differential equation. So we will have three variables, and we need to rewrite this equation using this variable. So this will be what? This will be y3 differentiation minus this is what? y2, right? Times y1, right? Plus 1. So this is this equation when we take these variables. Any questions about that? Because this is something that you need to understand how to do it. So I took this and put here, right? Took this and put, where is this? Sorry, it's, oops, my fault. Oops. Do it once again. So we need to put y1 here, right? Need to put y3 here, so here should be y3. Y3, and this is it. So I took derivative of the y3. Is that clear? Okay. So having only one equation, right now I will have a system of equation. So this is the something that you need to be aware of, that if you have a higher order differential equation, I mean higher than the first order, right? You need to expect that your system will be larger than original one. Because right now you need to write these additional formulas that describe relation between variables, right? Before you had this one, but you write in the form of the first order. So unfortunately, the dimension of the variable will be larger. So instead of one, you will have one y, this is first, two, and three. So this, I mean, this is something quite important, right? I mean, the thing is that if you have, right, this is the simple solution, example, sorry, simple example with only one variable, but the system, real systems can be much more difficult, and we'll have number of states, right? Your state vector will be like x, y, phi, I don't know, some can be large state vector, and if the equation that describe the evolution of the state is higher order, then your system will, the state will be much larger, right? You will have first derivative of everything, second, and so on and so forth. So the system at the end will be quite large. So this equation become a system of differential equation, and you need to write this part which is dependent on the which describe the dependency of the new variables, and this is the chain that I just mentioned before. And the last equation is in fact that you rewrite this equation. Always on this side we have the first order derivative. This is our y3, right? We had y3 y1 plus 1 is equal 0. So we need to write this in this form. So we need to have this on the right hand side. Sorry, left hand side is equal to plus y3 y1 minus 1, right? And this is the equation that we can put here to have on the left hand side the derivative, and on the right hand side have the dependent variables. That's it. Okay. Mm, well, I would like to raise this again, that this is something you need to really understand how to do it to move forward with the labs. So if you have any doubts right now, just ask, okay? Because during the lab it can be a little bit too late for this kind of questions. Okay. We are discussing the differential equation, solving the differential equation in this form, right? You can have some external parameters. And you know that you need to write the equation in this form, and in most cases this is doable. There is one issue with the numerical solvers designed for solving the ordinary differential equation, the initial value problem, and this is something we call the stiffness. And the stiffness is a little bit problematic for the engineers because there is a lack of a precise definition. What does it really means that system is stiff? And if there are no precise definition, you can't check in advance if your system is stiff or not, right? Because you would like to know before you select proper method if the system has this in fact we should say suffer from this problem or from this issue, because this is the issue. Let's try to explain what the in fact the stiffness, how we can describe the stiffness. So stiffness occurs when there is a difference in scaling somewhere in the problem. So it means that two components that drastically has different dynamics in the time scale. So let's say we have a system which evolve in time. Let's say x, we have 2x, and have y, which is 1000x plus something. So the dynamics of those two parts are very different. So it means that to properly calculate the distance at each point, you need to perform very small steps to properly estimate the first derivative and to select the direction in which you will follow. Um, and this results in this that solver probably will force down the steps to uh, very small number, and you will need to perform many steps, really thousands or millions of steps to find the solution, even on very short time period, right? So depending, this is your time period, let's say this is 0t, and smaller step is you need to perform much more steps to get from 0 to t, right? So this is somehow crucial to how large the step is, because it depends how fast you will get the solution. So it also means that if you will take the solver which is not designed for the stiff system, and you will provide the system which is stiff, and you will ask, okay, give me the solution or solve it, it will take ages or a very long time to provide this solution. And you need to know in advance, for this reason, you need to know in advance if your system is stiff or not, to properly select the right solver for it. Um, um, when you when you when you let's say do it on your PC, on your desktop, it's not a big problem. You can wait a bit longer, right? Or you can stop computation at any time. But if you have equation somewhere built in the machine that works, operates somewhere, right? And some of the parameters of the system evolve in time because, I don't know, it adapts to some external conditions. And at some point, you may reach the situation at which the system from the not stiff becomes stiff. And your solver, which was good for the non-stiff system, became not good for the stiff. And let's say you won't be able to deliver a solution in the, let's say, 10 milliseconds, right? And this will break the whole control system. And this is something problematic. Um, um, yeah, this is something that is somehow related to what I just said. Generally, the, those numerical solvers, they work like that. If you have smooth function which has very, I mean, low velocity in terms that the rate of change is small, the solver can perform large steps. So sometimes even in few 5-10 steps you can get to the solution on quite large time horizon. More curvature we have in the solution, or more this rate of change is higher, the solution, I mean the solver, needs to take smaller and smaller steps to get to the solution. And with the stiff system, the problem is that you can have very slow function, but even though because the system is stiff, the solver will take very small solution steps because of this difference in the rate of change of some internal dynamics. So this is why it's a problem for the engineers. So at the end, there's no non-stiff solvers are there are two cases. They are extremely slow, and this is this better case, or at the end they may have problem with find the solution, because each solver has some parameters which explain or which describe what is the minimum step it can take, when it should stop, right? Because in some stop condition, we need to at least know when to stop to avoid infinite loops, to guarantee the delivery of the solution on time. So in case of stiff solvers, sorry, non-stiff solvers for stiff systems, solver probably may be also not possible to deliver the solution. So it can be slow or even won't find the solution at all. Um, yes, this is some technical thing that maybe it's worth to mention that um, the reliability of the and efficiency of the solver can be improved by providing the Jacobian matrix or the sparsity pattern, but those are technical stuff, and I don't want to get into details right now. Just mention that there are some methods or ways how to improve the the overall performance of the solver. Okay, so this is the general stuff we discussed. Right now, let's see what kind of solvers we have in the Matlab, and a lot of those solvers can be easily found also in the other libraries or other frameworks, because those are mostly standard methods for solving the ordinary differential equation, so they are quite common. Uh, so knowing those with MATLAB, probably, I mean, it will be quite easy for you to switch to other programming languages, because probably you'll find quite similar methods or libraries in other frameworks, and the all expectation and the performance will be similar. So we need to provide quite the same inputs, and the output will be very similar. So knowing one of this implementation probably will give you the possibility to use also other implementation quite easily. Okay, so the first two, um, maybe, okay, before I jump here, maybe I should also mention one important note that uh, we have something, there are two things that describe the solvers. First uh, is the uh, order. So the order means how many points the solver evaluate the function to compute to estimate the derivative. So if you see that order is 4 or 5, or if you have a solver 45, it means that it will evaluate, or it will use 4 or 5 points to evaluate the derivative, but it doesn't mean that it will take 45 points. And 4 and 5 means that it will evaluate in 4 points or in 5 points, depending on the rate of change of the function. So if function is slow, typically solver just evaluate in 4 points, and the other thing is step length dt. So this is the second thing that solver can change. And we talked that solver is multivariable, multi-order, multivariable. It means that it can change order, so change in how many points it computes the derivative, and also about the step length. So it means that the step length from iteration to iteration can be smaller or larger, can vary. It's not fixed. Sometimes, in most cases, it's the feature to have those two things, that we switch the order and switch the step length. But there are some cases which we would like to know what is the step length and how many times you evaluate the function. Why we want to know that? So the thing is that sometimes the evaluation of the function is time consuming. Like you need, I don't know, 1 second to evaluate this function once, right? So depending of the order of the solver, the one iteration can take 4 or 5 seconds, or even longer, depending on the solver. Um, so this is one case. If the evaluation of this function is long, we need to know the worst case. So what is the longest time that solver needs to deliver a solution? And sometimes we fix that, okay, let's evaluate only at 4 or evaluate only at 5 to guarantee that this time is fixed, that it's not changed. This is important in real-time systems. When you have real-time system, you need to guarantee the worst case. And this is also the true for step length. So in the real-time system, you have, let's say, 1 millisecond to deliver a solution, but you compute solution on the, let's say, 1 or 2 milliseconds time period. So it means that you need to know how much iteration, if you know how much time you need for one evaluation of the function, and you compute how many iteration system perform, you can estimate the worst case time, right? But if this can change and the step length can change, you can get iteration in half millisecond, but you can get also the solution in, I don't know, 10 milliseconds. And in this case, it's something that you can't allow for, because you need to get solution in 1 millisecond. Then what you need to do, you need to use fixed step solver. And all those solvers that I will discuss here, or which are listed on this slide, those solvers are multi-step, multi-variable, multi-step solver. So they change order and they change the uh, step length. Okay, so the first two are the most basics. And in fact, the ODE45, this is the standard solver, which it should be your first choice. So if you don't know what kind of system you have, or you would like to just try something, you should try to use ODE45. And generally, it's designed for non-stiff system. Accuracy is medium. So, okay, maybe one more thing about solvers that I should another side note. Sorry for that. What is the problem with the numerical solution of the system? So we have an equation, right? Whatever, and it evaluates in time, right? Somehow, and this is how it evaluates. I mean, if you will take, if you are able to compute this analytically, this is the original solution. But the problem is with the iterative method that at each step you make some error. So instead of being here, you are here. So longer you um, longer you integrate, you get the largest error at the end. So you diverge from the I mean the original solution. So longer time frame you have, longer you integrate. In each step, you do some numerical round off. You have some numerical error, which is also related to the method you are using. And at the end, you get larger error. And this is a cumulative error. So you sum the errors from each step. So let's if E is a step, so this will be the final error will be sum of those all errors from each step. This is why we change this order, because for higher order we estimate the derivative better, and we perform, or we in fact have lower error estimation. Sorry, lower velocity error estimation. So the accuracy is medium. So this is the one of the parameters which you need to be aware of, that selecting the last order solvers, you will get the lower accuracy. Having higher order solvers, you probably can expect better accuracy. So first selection is ODE, and it's good solution, a good solver for most of the problems. Sometimes if you have computationally expensive uh, function, or for some reason ODE 45 is not good, maybe it's you can try the ODE 23. It behaves a little bit better for the Steve system, but not very good. I mean, a little bit better, right? So this is why, I mean, what you can try to do in the case when you have this kind of system. Um, the next one is also for non-Steve, and as you see, it can vary from 1 to 13, the order, so you can have very low or very good accuracy depending on the problem. Um, Sometimes it's more efficient because it starts with the lower order, so it can get to the solution faster. Uh, And this solver can be also used when the evaluation of the original function is quite expensive. The next two, in fact, three solvers are designed for the Steve system, and they use totally more advanced methods for solving the original problem. The accuracy is, as you see here, depending on the method. Um, This ODE 15S is also designed for algebraic differential equation. So with the solver, you can solve the DEAs. Um, the difference between those solvers are specific, so maybe I don't get into details right now because you will need to be more familiar with the kind of problems you deal with. I mean, you can back to this table later if you will deal with this kind of problems. This table is taken from the MATLAB help, so you can find those information also there. Um, what is worth mentioning is what is we had one solver for implicit, yes, exactly. So this one is um, is the solver. As you see, there is only one solver which deals with the implicit function, right? Um, and it's what it's also for DEAs, so it's quite advanced solver. The accuracy is low, and you probably can expect lower performance in terms of the time. The time needed for solving the same problem will be higher in those cases than in those cases. So those solvers are quite simple and good in most cases, but if you have some problems, then you should switch to different solvers. You shouldn't start with those solvers from the beginning. I mean, you can, right? But you will wait for the solution much longer, and the accuracy can be not so good as you expect, right? Um, okay. So this is the solvers. So most of those solvers has the same API. So you will be able to change the solvers very easily by just calling different method, but the API, I mean the arguments that you pass to the function are the same for all those methods, all those solvers. And here we have the API of the Matlab solvers. So we select the method, we provide the parameters and expect some solutions. So this is how we typically get the solution. We get the vector of times at which we get the and vector of solutions, right? So for proper time, we get proper solution. Or we can also get the object, solution object, and I mean, investigate some of the values. I mean, in fact, we can interpolate any. Uh, I mean, we can get solution for any time with use of the interpolation. So you can using this solution object, you are not somehow restricted or limited to this time at which the solution was sampled. There are also some additional features I will talk in a minute of the solver, um, and you will discuss this a little bit later. What is important for us is the inputs. What do we need to provide to solve the ODE? So this is the something you need to be aware and how to use it to proper deal with the issues during the lab. Okay, so as I said, those solvers solve the first order differential equation on some time horizon, uh, starting from initial conditions. So we solve the initial value problem here. And the first argument you need to provide is the function which describes the right-hand side. So this is a right-hand side of the equation. So this is this. This function, so we need to write, typically we write the new m file, right? Like it needs to return the state, I mean this y prime, right? So this can be a vector of solutions equal f, and the first argument is time always, and then we have the state. Okay, let it call y dy. So this is typical API for the function or for the right hand side. Right hand side needs to be in this form. So the first argument is time, second is the state at given time. So this is y at t. So solver provides time t, and at this time provides the y. And what you need to calculate? You need to calculate the dy, the vector, right? D whatever dn is equal to your complex system, and this is what you return back, right? Is this clear? This is very important. This is standard for the ODE's function. ODE's function assume that this function will have this form.
Does the order of this left-hand side dy dt is important?
I mean,
with respect to ty on the right-hand side.
Yes, well, this is the state, right? So what you need to preserve is the order of the, sorry, let's call it d, right? So if you have some function of time and y1, so this is how it works, time y2. So this is system of equation. So the order, so if when you have your function f, right, and time, so here we will get also the vector. So the solver will give you the vector of y's, the state. It will be the state of the system. And you need to compute the result also in the same order. You can't mix those, the order of dy's needs to be the same like the order of y's in the input. Okay, is this answer your question? I mean, this is, standard, right? I mean, this is what you should expect, that you shouldn't mess with the order of variables in the vector. So if the order of the input is y1, y2, and so on, the d1, d2 should be the same. You need to remember that the first argument is time. It doesn't mean that you need to use this time in your function in the right-hand side, but it needs to be there. So when you define this function, right? Function, whatever, equal fun. So even if you don't use it, it needs to be there, right? So dy is equal y, or 2 times y, whatever. Even if I don't use it, it needs to be there. You can't omit this parameter in the definition of function. Okay, so this is written here. What else? We have what, 3 minutes, right? Not good. T-span is the interval. So this is another next argument, right? First is the function. I mentioned that this needs to be function, right? So we need to write a separate script. So fun.m and have those stuff in this file. But what you can do, you can provide also the function handler. It does need to be. I mean, this can be function handler or can be name of the function you want to call. So the next argument is the t-span. So this is the time at which we define the, we ask for the solution. This is this time horizon. And it needs to be a vector. So there are two methods. The first one, so you provide the initial time and the final time. And in this case, if there is only two elements, at the end, at the output, the solver will give you t and y's, not only two, but you will get number of those times and number of y's, depending how the solver, what was the steps length and what happened in the middle. So you can't assume anything about size of the output. But if you provide this time interval in the form of the vector longer than 2, so then at the output you will get this vector, and the y's will be sampled at those times. So you will get the solution exactly at the time you ask for. Okay, so it's up to you what you need. Sometimes you don't care, right? Because you just don't care. But if you want to, let's say, plot nice the evaluation of the system, right? So you want to have very smooth path. So it's better to ask for specific points, because then you will have very smooth plot. Otherwise, you can have jumps in the, can have a long jumps, and the plot won't look good. It depends on the use case, in fact. Okay, what do we have there? What next? Yeah, another important thing, maybe what we should mention is that you can integrate forward in time, right? But you can also integrate backward. So you can say that this is some final time and this is initial time, and solver will integrate from starting from the end till the beginning. This is also possible. And sometimes this is useful in estimation, let's say, when you need to estimate. So you are at some point, right? The system has evolved in time, right? And this is time when you do the measurement. You measure the state here, right? This is your x. But you want to estimate what happened in the past, what was the parameters of your system, that the system has evaluated to this point. Probably you have some parameters, you have some control. So you know this control, you don't know parameters, and you want to estimate the parameters. So we call this moving horizon estimation. And in this case, you need to integrate backwards to estimate what was you need to somehow recreate what happened in the past to find, okay, what was the parameters that we get to this point which we are right now. But this is some specific stuff. Okay, we unfortunately run out of time. I need to stop here and we'll continue next week. Any questions? Something we should discuss before the end? I think that this, what I just said, will be probably enough to play with the task on the labs. Let me check it again if I haven't missed anything important. Yeah, maybe this initial condition, but this is, I think, clear, right? This is vector which you provide, which you start, at which you start integration, right? So you need to provide the state of the system from which you start integrate and look for the solution. But this is something I hope clear. So this is basic, and the other things are, yeah, those are more. Yeah, those events are, and here is an example how you can solve. So you can look at this example. As you see, we use the function handle here. We don't specify the external function. So this code is for solving this differential equation on this time frame, starting from this initial condition and with applying this kind of control. And we look for the solution. So we would like to see how the system evolves, and this is how it looks. So here we have a trajectory, so how the state evolve in time, and this is the path. So when you draw the Q1 and Q2 on the plane, so this is how this robot has been moving. Yeah, but this we will continue during the next lab. Okay, that's it. Thank you very much. See you on Friday.
Thank you. Have a nice week.
Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you.